Okay, so now we're going to take a look at one of the applications of the definite integral. If you take more calculus, if you go on to take Calc 2 and even also Calc 3, you're going to do a lot of applications of integration, and they're almost all definite integrals that we use. So the two that we're going to look at in this chapter are areas by integration, which we already have some experience with, and then also finding a volume of a solid of revolution. So we'll get to that part later, but first, these areas. We've already learned how we can use integration to find the area under a curve. And when we talk about the area under a curve, we are really explicitly assuming that this curve that we're interested in, exists above the x-axis, right? And so this area, if this is y equals f of x, this area we said was going to be the integral from a to b of this function. We're going to look at this some more and then generalize it to just regions in general in the plane that are bounded by functions, and we won't be quite so tethered to the x-axis as we currently are. So here's how we find an area by integration. The first thing, always, 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 I cannot emphasize this enough, you had better sketch that region. Either throw it in the calculator, make sure you know what it looks like. I mean, I write it out twice here. Down here it's in all caps. I am highlighting it. I cannot emphasize enough that we cannot expect to get an accurate result if we don't understand what the region looks like. So in these problems that we see, they're going to describe a region, what a region is bounded by, and then they'll ask us to find the area. So we're going to make a sketch. Then the next step says draw a representative rectangle. This means, pretend for a moment that you're approximating with rectangles, right? But only draw one rectangle. And what might a rectangle look like if we were approximating? If that representative rectangle that you draw, if you can get an expression that gives you the area of that one rectangle, then the integral practically writes itself. And so that's why I make such an emphasis out of sketching the region and drawing that rectangle. So here's just the general situation. And again, I have sketched it so that this function does exist entirely above the x-axis. We will generalize in a bit. But let's say we have this function y equals f of x. Now, if I were to pretend here that I wanted to approximate with rectangles, one such rectangle might look like this. I'm just drawing one. There's a representative rectangle. Now, this width that this rectangle has is an x width. It's like a horizontal width. That's a delta x, a change in x. And the length of this, because it's bounded in this generic model here, bounded by the function in the x-axis, this length is f of x. In general, the length is always going to be the top minus bottom. A vertical length is always top minus bottom. So the area of the sample rectangle, or representative rectangle, whatever you want to call it, I call that delta A. So delta A, just the area of that rectangle, is length times width. That's f of x times delta x. Now we use this and we get the integral. So the area, no longer a delta A, but A, is the integral of f of x. And then the idea here is that this representative rectangle, I'm using infinitely many of these representative rectangles. And they're all infinitesimally small, narrow, so that delta x shrinks down to 0. And when we do that, this delta x we call dx. And the boundaries of the region are the limits of integration. there's a connection physically between like these physical bounds of the region and those limits of integration that we use. And the idea behind that is this representative rectangle, this sample rectangle I drew. I want to think about how far over to the left could I push that rectangle? How far over to the right could I push that rectangle? I'm imagining that that rectangle can kind of travel or slide, you know, left and right, and how far over. So these limits of integration really are physical boundaries, and so we integrate from A to B. Okay, let's do an example. All right, so we're going to find the area bounded by the graph of y equals 2x squared, y equals 0, x equals 1, and x equals 2. And often, you know, sometimes they provide you with a sketch and sometimes they don't. Here we happen to have a sketch of the function y equals 2x squared, just a part of the function, right? It's just the first quadrant region, but it's the part that we're interested in. So 2x squared, y equals 0 is the x-axis. X equals 1, x equals 2, those are these vertical lines. So we end up with the region now that looks like this. So I want to make sure I know what this region looks like. And if I were to approximate this area using rectangles, I would draw a rectangle that looks probably, I don't know, something like this, right? A nice vertical rectangle here. This vertical rectangle has a width of delta x, and this length, which we always get a vertical length by taking top minus bottom, is 2x squared minus 0, or 2x squared. So the area of the sample rectangle, delta A, is 2x squared times delta x. That's length times width. And that means that the area itself is the integral of 2x squared dx. And the limits of integration come from the physical boundaries of this region. How far to the left could I push that rectangle? How far to the right could I push that rectangle? So we are going to integrate from 1 to 2. Now we can integrate. Now this we've taken this area problem, turned it into a definite integral problem, and that's going to give us. Now we know how to integrate this, right? It's a power rule integral. So the result is 2/3 x cubed. We're going to evaluate this from 1 to 2. So 2/3 times 2 cubed minus 2/3 times 1 cubed, which is 8 times, that's 16/3 minus 2/3, or 14/3. Now, one thing to keep in mind when you're doing an area problem is that areas of regions are always positive. If you set up the integral correctly and you integrate correctly, it will be impossible for you to get a negative area. So now, if you find, you know, we got a positive area, everything worked out well here. If you find that you get a negative area, what that means is there's a mistake somewhere and you should find it. It does not mean I got a negative area, so I'll just change my answer and make it positive. Don't do that. It's an indication that there's an error somewhere and you should try to find it. So in this example, you know, we drew this rectangle. It was a vertical rectangle that had a delta x width. There are scenarios in which we might draw rectangles, horizontal rectangles, to help us model our region. What's important here, if we just look at this particular example that we finished, this vertical rectangle, no matter where I draw the rectangle, I could draw it over here or over here, right? Or maybe somewhere closer to the middle. I would always get the length. The length changes, but I always get the length by doing the same thing. I get the length by taking the function 2x squared and subtracting 0. So the rule I use to find the length doesn't change as I move the rectangle throughout, and that is what is really important. Sometimes we need to use horizontal rectangles in order to make that work. And just, in this generic scenario, suppose I have a region that looks like this. We'll note right off, I can't use vertical rectangles. If I try to use vertical rectangles, then drawing a rectangle over here on the left is bounded above and below by the vertical lines. But as soon as I slide the rectangle over here, the boundaries change. The top boundary stays the same, but the bottom boundary changes. So I can't say that top minus bottom, the rule that I would use to find the length of the rectangle is the same throughout. It actually changes. And so for scenarios like this, we need to use a horizontal rectangle. A horizontal rectangle. Now the width is a vertical width, so that's a delta y width. And the length is a horizontal length, which means it's going to be the right x minus the left x. And in this case, that looks like g of y minus 0, or just g of y. The area of the sample rectangle, our delta A, length times width, now is g of y times delta y. And so when we make our integral out of this, we're going to integrate the function g of y. And now that delta y, as it shrinks down to 0, becomes dy. We are integrating with respect to y. And that's why it's important that we have a function of y. We don't want to integrate x's with respect to y. We need to integrate y's with respect to y. And because we're integrating with respect to y, we need y limits. And just like with the other scenario where we use vertical rectangles, our limits are going to come from the physical boundaries of the region. But this time, if I'm drawing horizontal rectangles, those boundaries come from above and below. How far down could I push that rectangle? How far up could I push that rectangle? And these limits now are from C to D. These are y limits. So let's do an example. Here we want to find the area of the region bounded by y equals 9 minus x squared, x equals 0, which is the y-axis, y equals 2, and y equals 8. So it's these horizontal lines, and then here's the curve, 9 minus x squared. So the region that is properly enclosed by all of the equations they give us looks like this. And we should just understand right off that, one of the first things we want to do after we sketch the region, and this is one of the reasons it's so important to sketch a region, is we need to know what kind of rectangles to draw. Are we going to draw vertical or horizontal rectangles? Vertical rectangles will not work because the rule that I would use to find the length of that rectangle is different than the rule I would use to find the length of that rectangle. The top minus bottom, the boundaries change. So we're going to use horizontal rectangles. Now note that if I use a horizontal rectangle and I imagine sliding this rectangle up and down through the region, the right boundary is always the curve 9 minus x squared. The left boundary is always the line x equals 0. And so that consistency means that drawing horizontal rectangles will work. The width is a delta y width, and I need this length. This length is, of course, going to be the x-coordinate of the curve, but I need to get that as a function of y. So let's do that first. Let's find x in terms of y for that curve. So if y is 9 minus x squared, that means that x squared is 9 minus y, And note this curve, we're just looking at the first quadrant region, so when we take the square root, we only need the positive root. So x is the square root of 9 minus y. X coordinate we know is positive. Okay, and that I'm going to bring back over here to the diagram. So that's our length, is the square root of 9 minus y. That's our right minus left, because notice that our left endpoint is 0, so we'll just be subtracting 0 to get that length. Now if I want to find, let's see, if I want to find the area of the sample rectangle, that is delta A, length times width, is the square root of 9 minus y times delta y. And now we can write the integral of the square root of 9 minus y dy, and our limits are going to be y limits, so they come from the physical boundaries, how far up, how far down we can push that rectangle. So we're going to integrate from 2 to 8. So now we have turned this area problem, we've expressed it as a definite integral, and we're ready to integrate. So just think about how to integrate this now. We're going to need probably to use a u substitution, because we have the square root of some stuff, right? That means we have this stuff to the 1/2 power. So we have parentheses to a power. So we're going to let u equal 9 minus y. That means that du is negative dy. We need a factor of -1 in here, and we're going to compensate by putting a negative on the outside. And since we've switched up since we're making a u substitution in a definite integral, it might make sense to also change our limits. Let's adjust these y limits to become u limits. So when y equals 2, that means that u is 9 minus 2, or u is 7. And when y is 8, that means that u is 9 minus 8, or u is equal to 1. So let's see what that gives us in terms of rewriting this integral. So I can't forget that I got the negative out in front. I'm integrating. Now my lower limit is 7. My upper limit is 1. This might feel confusing because 1 is a smaller number than 7, but those correspond to the lower and upper y limits. So we're integrating from 7 to 1. U to the 1/2 du. Now this integral is a power rule integral, so I'm going to bring the negative sign over. If I integrate u to the 1/2 using the power rule on that, I get 2/3 u to the 3/2 power from 7 to 1. And now actually I'm going to do, I think, one thing that'll kind of help simplify this. I have this factor of 2/3 on the result of integration here. I'm going to just pull that factor out. So we got a negative 2/3, and then inside u to the 3/2 from 1 to 7. So I'm going to plug in the upper limit first, minus the lower limit. So as an exact result, this is what it looks like. But let's get an approximation here. We get 11.68 approximately. Okay, so far all the regions, here's this one we just finished. This is bounded by a curve and the x-axis. The other example that we did was bounded by a curve and the x-axis. Sorry, this one was bounded by a curve and the y-axis, the one we just finished. This one was bounded by a curve and the x-axis. So they ended up being integrals of just integrating our function and needing to find the right limits. But we might also, in fact we will also, encounter problems where we are interested in finding the area bounded between two curves, not just a curve and one of the axes. But our approach will move flawlessly into this more general problem. So again, always sketch the region. I cannot emphasize that enough. You want to make sure you know what the region looks like, in part because you need to know if we're going to draw vertical or horizontal rectangles. And the way we decide is, as I imagine, this rectangle that I draw, as I imagine sliding it, if it's a vertical rectangle, I have to imagine sliding it left and right through the region. I need the boundaries, the top and bottom boundaries, to always be the same. If it's a horizontal rectangle, if I'm using horizontal rectangles, it needs to be the case that as I slide it up and down through the region, the right and the left boundaries remain the same. Right? So there has to be some consistency with how I find the length of the rectangle. And when you're finding the length of a vertical rectangle, it is always, as we have said before, the top y minus the bottom y. Right? Top curve minus bottom curve, that gives you a vertical length. If you've got a horizontal rectangle, you get a horizontal length by taking the right x minus the left x. And in these cases, right, the right x and the left x, those are functions of y. And up here, the top y and the bottom y, those are y as a function of x, right? So we're always integrating x functions with respect to x. We're integrating y functions with respect to y. Here's an example. We want to find the area of the region bounded by these curves y equals x squared and y equals x plus 2. So if, the first thing we would do is graph it. Here's a graph has been provided, but if one weren't, the first thing we do, you could sketch them out by hand. You could throw them in the calculator. You just want to make sure you know what this looks like. The region, there is one region that is kind of properly defined by these two curves, and only these two curves, and that region is this one right here. So now that we know what this looks like, our next step is, do we use vertical or horizontal rectangles? Now take a few seconds and try to imagine what it would look like if we use vertical rectangles, what it would look like if we use horizontal rectangles, and if there's one choice that would work better than the other. So when I look at this, I can tell that horizontal rectangles will not work. And the reason they won't work, or they won't work easily, they won't work without a lot of extra work on our part, is because a horizontal rectangle drawn up here has the right boundary as the parabola and the left boundary as the line, but as I move down here, the left boundary changes from the line to the parabola. And that's going to be a lot of extra work if we wanted to try to do this with horizontal rectangles. Vertical rectangles will work because as you imagine sliding this rectangle to the left and to the right, the top is always the line, the bottom is always the parabola. So there's our delta x width. The length here, top minus bottom. The top is the line x plus 2 minus the bottom curve x squared. And I'm a fan of writing polynomials with in descending order of exponents, so I'm just going to write this as negative x squared plus x plus 2. So now we can write the expression for the area of the sample rectangle. So delta A, length times width, is negative x squared plus x plus 2 times delta x, length times width. And from that, the integral practically writes itself. We're going to integrate negative x squared plus x plus 2 dx. The only thing we're missing right now are the limits. Now the limits come physically from the boundaries, like how far to the left I could slide that rectangle, how far to the right I could slide that rectangle, and in this sketch we could tell that those limits are really defined by these intersection points. So we're going to find the intersection. And to find where two curves intersect, I'm just going to set those functions equal to each other. So we want to know where is x squared equal to x plus 2. This is a quadratic. X squared minus x minus 2 is equal to 0. I think this will factor, but you could also use the quadratic formula or complete the square if you like. Minus 2 plus 1. So we get x equals 2, x equals negative 1 for our limits. And that seems to jive, right? That kind of looks like where these line up here. So we're going to integrate from negative 1 to 2. Whoops, negative 1 to 2. And now we can go ahead and do the integration. It's the power rule the whole way down. This is a polynomial, so negative 1/3 x cubed plus 1/2 x squared plus 2x from negative 1 to 2. We're going to plug in the upper limit and then subtract what we get when we plug in the lower limit. So from here, from this point on, if you just throw this expression in the calculator and get a final result, that's fine. I do want to see you actually plugging in those limits into the expression. But from here, if you just say, oh, I'm going to throw it in the calculator, get a final result, that's okay. If you do that, you're going to get 9/2 for the area. Okay, let's try another. We're going to find the area of the region bounded by x equals 3 minus y squared and y equals x minus 1. Now you'll notice that one of the functions they gave us, x as a function of y, it kind of makes sense, right? It's a sideways parabola, so you know y would be the squared variable and x is not. But if you look at this region, again, if we outline the region that we're interested in here, that's this right here. There's one region that's sort of properly bounded by just the equations they gave us. And again, take a few seconds, see if you can tell whether vertical or horizontal rectangles are better, and pause it if you don't want to hear me say, pause it if you want to give yourself more time. So in this problem, you're really going to want to use horizontal rectangles. Vertical rectangles won't work because over in this part, it's the line minus the parabola, but over here, the top and the bottom are both the parabola, and that's not really well-defined bounds. It would be a lot more work to do this with vertical rectangles. So what we want to do is use horizontal rectangles. If we do that, here's what a rectangle might look like. And as I imagine sliding this rectangle up and down through the region, it's always the parabola on the right and always the line that's on the left. So while the length of the rectangle definitely changes, the rule that we use to find the length remains consistent. So the width is a delta y width, and this length is right minus left, and it's the right x minus the left x. So the right x is the parabola, and as a function of y, that's right here, 3 minus y squared, minus the left x. So what we have to do is take this and solve it for x, or rearrange it, which doesn't take much work. There, x is equal to y plus 1. So we're subtracting y plus 1. The parentheses here are absolutely crucial. I have to make sure I'm subtracting the whole function. So don't forget your parentheses when needed. It can be easy to make sign errors when you're finding areas. I'm going to simplify this expression. And again, I like to write my polynomials in descending order of exponents. So a negative y squared minus y, and then 3 minus 1, that'd be a plus 2. There's our length, and our width is delta y. So delta A, the area of our sample rectangle, negative y squared minus y plus 2 delta y. That means that the area integral practically writes itself. We're going to integrate negative y squared minus y plus 2 with respect to y. The delta y turns into a dy. The only thing we need are our limits, and yeah, I think you guessed it, we're going to have to look at, to get those physical boundaries, we need to find those coordinates where they intersect. So to find where two curves intersect, I'm going to set those functions equal to each other. Or really, actually, let me be a little bit more general, because they didn't express both functions in the same way, right? One, we have y as a function of x, and the other x as a function of y. We're going to treat these as a system of equations, right? We have two equations and two unknowns. Although we do have, now they gave us this one, x as a function of y, and then we did rewrite this one. So I can set both of these expressions of y equal to each other. So I want to know, where is that expression y plus 1, where's the line equal to the parabola 3 minus y squared? And if I get everything on one side, again, it's a quadratic. So I'm going to get everything on the left side, y squared plus y minus 2 equals 0. And if we factor this, I think it'll factor, but you could use the quadratic formula or complete the square. Y and y plus 2 minus 1. So we have y equals negative 2, y equals positive 1. Those are our limits from negative 2 to 1. Now the definite integral is finished, right? So we can evaluate. Negative 1/3 y cubed minus 1/2 y squared plus 2y from negative 2 to 1. I'm going to plug in the lower limit, the upper limit, and then subtract what I get when I plug in the lower limit. And now if you throw this expression in the calculator, you should get 9/2. Again, I guess I was a fan of that result when I wrote up these examples. Okay. We're going to finish this section with one more example, which is going to illustrate how sometimes we'll just have to approach an area problem maybe with a couple of different integrals. A single integral doesn't always do the job for us. So they've asked us to find the area of the region bounded by, and then they give us these two polynomials. We have a cubic and a quadratic. Now, there is a region bounded, but it kind of is split in two parts. So we've got this part here, and we've got this part here, and we want to find that whole area. Okay, so for either one of these areas, I think we could do the job with vertical rectangles. But a single vertical rectangle, a single integral won't evaluate this, because if I look at on the left here, right, so there's a delta x. On the left, you know, top minus bottom is the cubic minus the quadratic. So that is 3x cubed minus x squared minus 10x minus a negative x squared plus 2x. And over on the right, again, a delta x with top minus bottom this time is the quadratic minus the cubic. So that's negative x squared plus 2x minus, and then subtracting this cubic. So what we're going to do to finish this problem is we're just going to approach these as two different regions, and then we're going to add them together. So I'll call the one on the left, I'll call this A1. The one on the right, I'll call this A2. If I simplify these expressions here, so on the left, the length for A1 is 3x cubed. Let's see, subtract a negative x squared, those go away. Negative 10x minus 2x is negative 12x. And over here in A2, top minus bottom, this simplifies to a negative 3x cubed plus 12x, which maybe we're not so surprised. When all you do is change the order of subtraction, the effect that has is it just changes the sign on your expression. So we have these two regions now. We know the lengths of of each rectangle. When we think about limits now, we're going to have to think about these points. There's 3 points we have to consider. 3 points where these curves intersect. So in the blue region on the left, we're going to integrate from this point up to the middle, and then this at that point in the middle is where the second integral is going to pick up where that one left off and integrate from that point down to this rightmost point. So let's find these limits. So we're going to set these functions equal to each other. 3x cubed minus x squared minus 10x equals negative x squared plus 2x. If I get everything on the left, I have 3x cubed minus 12x equals 0. We could factor out a 3x, and then we have x squared minus 4. And then x squared minus 4 is a difference of squares, so we could factor that as x minus 2, x plus 2. And we have three factors, 3 spots where this product could be 0. So 3x is 0 means x is 0. And then this gives us x equals 2, and this gives us x equals negative 2. So one integral will go from negative 2 to 0. The second integral will pick up where that one left off and integrate from 0 to 2. So for the A1 region, let's start on the left. Delta A1, length times width, 3x cubed minus 12x times delta x. That means that A1 as an area, we're going to integrate, again, those limits, negative 2 to 0. 3x cubed minus 12x dx. If I think about the right side, we're just going to set up these integrals first. If I think about on the right side, our delta A2, the area of that sample rectangle, negative 3x cubed plus 12x delta x. And so that area is bounded by from x equals 0 to x equals 2, so those are our limits. Negative 3x squared plus 12x. Negative 3x cubed, sorry, plus 12x dx. We've got both of the integrals set up. They're both going to be relatively simple to find just because they are polynomials. So we don't have to do any substitutions, I guess. That's what I mean when I say relatively simple. We always want to make sure that we're being careful when we do the integration. So applying the power rule, we get, let's see, increase the 3/4 x to the 4th minus 6x squared. This is from -2 to 0. Now if I plug in 0, you know, every term is a factor of x. So if we plug in 0, we are going to get 0. So that won't be a surprise. And then we're going to plug in -2. So this part zeroes out. I'm going to use the calculator to find that, and then whatever I get, I'm going to change the sign because I know I'm subtracting it from 0. So that's a -12, but I'm subtracting -12, so this is +12. Now over here, a2, very familiar integral. It's the one we just did, only the signs are different. So we have a -3/4 x to the 4th plus 6x squared. From 0 to 2. So we're going to plug in the upper limit first. And then the lower limit. Of course, when we plug in 0, that will just give us 0. So let's plug that into the calculator. And we get 12. Okay, so A1 and A2 are both 12, so the total area, which is their sum, is 24.